Hello girls, welcome to the binomial distribution part 2. So in this lesson we're just going to look at a few examples, 4 of them I think, and we will then move on to an exercise to practice this method. Right, example 2. A biased coin a bias means that it doesn't fall equally either on heads or tails. One side is particularly weighted. Right, so a biased coin is tossed 8 times. The probability of getting a head is 2 out of 3. What is the probability A, exactly 5 heads appear, or B, at least 2 heads appear? Right, so we asked for A, exactly 5 heads appear, so we're going to let X equal the number of heads that show. Okay, or just the number of heads. We also know that n equals 8 because there are 8 tosses of the coin, and the probability of getting our successful outcome is 2/3. So for this question, we need exactly 5 heads. Okay, so given that you already know that our general formula we worked out in the last lesson is as follows, we can substitute the given values that we've just written into this formula. Okay, so we're going to have now the probability that X is 5, and we're going to have 8 choose 5 times 2/3. That's the probability of success. 5 times 1/3. Remember, 1 minus P to the power of 3. Remember those two exponents. The 5 and the 3 must add up to 8. Right, so that gives us 8 choose 5 gives us 56, which basically means that there are 56 different ways to get 5 heads from 8 flips. All right, and then times the 2/3 to the 5th. Sorry, let me fix that up. 2/3 to the 5 times 1/3 to the 3rd gives us a 0,2731, which is about a 27% chance. Okay, question B. At least 2 heads appear. So for at least 2 heads to appear, that means that we need to have, or we could have 2, 3, 4, 5, 6, 7, 8 heads. So it amounts to finding the probability that our random variable is greater than or equal to 2. That's what we need to look for. Okay, so it can be 2 or anything higher than that. It just can't be 1 or 0. However, it would take extremely long to work out all of these exact probabilities, so there's an easier way. Remember, the sum of the probabilities of a random variable must always be equal to 1. So that means that the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus, and all the ones in between to the last one, the probability that x equals 8 must equal 1. So from that, we can state that the probability that x is greater than or equal to 2 must be 1 minus the probability that x equals 0, because remember that's not allowed, plus the probability that x is equal to 1, because that's also not allowed. Right, so developing that further, we can then substitute the actual values. So the probability that x is 0 will be 8 choose 0 times 2/3 to the power of 0, because there's no heads in this case, times 1/3 to the power of 8. In other words, they're all not heads, they're all tails. And then to that we add the probability that x is 1 will be 8 choose 1 times 2/3 to the power of 1 times 1/3 to the power of 7. All right, putting that onto our calculator, we get a 0,9974, which is roughly a 99.7% chance. So an important idea that comes out of this example is that the probability that x equals 0 plus the probability that x is 1 plus the probability that x is 2 plus however many probabilities we have, so let's call it n, up to n trials or whatever it is, will always equal 1. All the probabilities must add up to 1. Remember, it's binomial distribution. All the probabilities must add up to 1. Example 3. A fair die, that means not biased, is thrown 15 times. What is the probability that A, 4 6s appear, B, less than 3 6s appear, and C, 3 or more 6s appear? Right, the first question you might have here is that how is this binomial? Because a die has 6 different options. You can throw 1, 2, 3, 4, 5, or 6. But remember what they're asking. If in A, they're asking for 4 6s to appear, then getting a 6 is a success, and not getting a 6 is a failure. So if you roll a 1, 2, 3, 4, or 5, that's a failure. So the binomial aspect comes into it in that we either throw a 6 or we don't throw a 6. So that tells us that P, in other words, the probability of a success, is 1 out of 6, and the probability of not getting a 6 will be Q is equal to 5 over 6. So for A, the probability that 4 6s will appear, we can show as x equals 4. And now remember, out of 15 trials, we are choosing 4 6s. Okay, multiplied by 1 over 6 being the probability of getting a successful outcome. There are 4 of those. And the other 11 out of the 15 will be not 6s, and so we represent that as 5 over 6 to the power of 11, because the probability of getting anything other than a 6 is 5 over 6. Right, and simplifying that, we get 0,14175, which is about a 14.2% chance. Let's look at B now. The probability that less than 3 6s appear. So now we're looking for the probability of x random variable less than 3, which we know must be the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2. Right, so let's just populate all of these. So for the probability of x equaling 0, we know that there are going to be 15 trials. Choose 0. Okay, remember, we're not looking at the dice rolling a 0. I just thought I'd need to emphasize this now. But we're looking at 0 6s occurring. All right, so that means that's then 1 over 6 to the power of 0, because 0 6s are occurring. But 5 over 6 to the power of 15, because all 15 trials then are not a 6. Right, then for the probability that x equals 1, we then have 15 choose 1, because 1 trial out of the 15 will now be a 6. So that's 1 over 6 to the power of 1 times 5 over 6 to the power of 14. And then for the last one, the probability of x equals 2, we are saying that we're now working with 15 choose 2. That means 1 over 6 to the power of 2 times 5 over 6 to the power of 13. All right, remember that these exponents always have to add up to the number of trials. So in the first group, 15 plus 0 is 15, 1 plus 14 is 15, and 2 plus 13 is 15. Right, punch that all into the calculator and you end up with a 0,5322, which approximates to about a 53% chance. Okay, and remember, just interpret your answer. It's a 53% chance that less than 3 6s will appear. In other words, either no 6s, 1 6, or 2 6s out of the 15 trials. Right, for question C, what is the probability that 3 or more 6s appear? So now what we're looking for is the probability that our random variable is greater than or equal to 3. So if we expand that based on the formula you learned previously, that means it's the probability that x equals 3, because 3 is included, plus the probability that x equals 4, plus the probability that x equals 5, all the way to the probability that x equals 15. Okay, all inclusive. Right, so obviously you don't want to add up all the way to the probability of your random variable equal 15, so we're going to look at it in a different way. Remember that the probabilities of all these values need to add up to 1. Okay, so if we look at the following, okay, so what I've said here is that the probability of x equals 0, 1, 2, 3, 4, all the ones in between, to the probability of x equals 15, we must know equals 1. Okay, now we can break this up into what we've already worked out. These first three, we already know that this is the probability that random variable x is less than 3. And we know that the remainder, up to the probability of x equals 15, this is the probability of your random variable x being greater than or equal to 3. Okay, so in other words, we can state then that the probability of x less than 3 plus the probability of x greater than or equal to 3, remember this leads on from the previous questions, must equal 1. So that means that the probability of x greater than or equal to 3 is equal to 1 minus the probability of x less than 3. And we've done this in the previous question. So we just need to substitute 1 minus the probability that we calculated in the previous question of x, your random variable x less than 3 is, and remember use your percentage in a decimal form here, is 0,5322, which gives us a probability then of 0,4678, which in percentage form will be 46.8%, that we will have 3 or more 6s appear. Alright, example 4. A bag contains 3 Smarties and 9 Jelly Tots. 7 items are randomly drawn, one at a time from the bag with replacement. What is the probability that we draw 2 Smarties? So it's quite important in an exam. Remember, they're not going to tell you that you're dealing with binomial distribution or hypergeometric distribution. So it's important to try and work out what distribution you're working with. And it can get confusing when you're dealing with something like this where there are 3 Smarties, there are 9 Jelly Tots, 7 items are taken. Is this still binomial? Okay, so let's see. There are 2 outcomes, either Smarties or Jelly Tots. After each sweet is drawn, we replace it back. So it means the probabilities remain the same on every trial. You will see that the probabilities change with hypergeometric, but that's in another lesson. Right, so we're drawing 7 sweets. All right, so in other words, it's the same as saying that there are 7 trials. Because after each sweet that we draw, we're putting it back. So the probabilities remain the same. Okay, Smarties will be the success outcome because they're asking us what is the probability that we draw 2 Smarties. Okay, so therefore that means that P equals 3 over 12. Remember, because there are 3 Smarties and 9 Jelly Tots, so it means that 3 Smarties out of 12 is our probability of drawing a Smartie. Okay, and we want to know how we draw exactly 2 Smarties. So that means we're looking at the probability that our random variable equals 2. All right, and that means out of 7 trials, we are choosing 2. And our success, or our p-value 3 over 12, means that the exponent will be 2, and our failure rate will be 9 out of 12, all the remaining sweets, and that will be to the power of 5, to give us a total of 7 if we add the 2 and the 5. Right, simplify this, we get 21, that's for the 7, choose 2, times 3/12 to the power of 2 times 9/12 to the power of 5. And that in total gives us a probability of 3,115, which is 31.15%. Just take note of how they ask you in a question paper to round off. All right, example 5, the last one for this lesson. It is quite a challenge. Clinical trials have shown that 1 in 5 patients are cured from a certain disease by a new drug. How many patients need to be tested so that the probability of curing at least 2 people is greater than 90%? Now, I'm sure, especially living through this situation that we are now with COVID-19, this kind of question becomes more realistic to us. Okay, so imagine that they're showing that their trials are that 1 in 5 are cured from COVID-19 by a new drug. How many patients need to be tested so that the probability of curing at least 2 people of COVID-19 is greater than 90%? All right, so what makes this binomial? We have 2 outcomes for each patient. Either they're cured or they're not cured. The probability of a patient being cured on any given trial is given as P equals 1 over 5. Okay, let me put that in a different color. There we go, magic. All right, so P is equal to 1 over 5, which is also equal to 0.2, depending on how you want to show that. And because we're looking at how many patients need to be tested so that the probability of curing at least 2 people, we're going to say let X equal the number of patients cured. Right, so we need to find N because they're asking how many. Okay, so that's what makes this a challenge. In other words, we're looking at the trials. How many trials have to happen? All right, so one thing that we can write, they said at least 2 people greater than 90%. We can write that as a probability that says the probability as X is greater than or equal to 2 must be greater than 90% or 0.9. So that's effectively what we have to work with. Okay, so I'm going to just say that again. They want us to see how many patients must be tested so that the probability of curing at least 2 people is greater than 90. Okay, so there's the probability. And the greater than or equal to 2 shows us the at least 2 people is greater than 90%. Okay, so using this, if the probability that X is greater than or equal to 2 is greater than 0.9, then that means that 1 minus the probability, sorry, lost my pen, 1 minus the probability of X is less than 2 is also greater than 0.9 because they're equal. 1 minus the probability of X is less than 2 is equal to the probability of X greater than or equal to 2. Okay, and then expanding on that, we can say that, well, the probability of X minus 2 is as follows. So 1 minus, let's open a big square bracket. We're still going to have the greater than 0.9 there. But the probability of X minus 2 is, sorry, X is less than 2 is the probability that X is 0 plus the probability that X equals 1. Okay, so now let's expand those two. Right, so firstly, the probability that X is equal to 0 will be N, choose 0, remember there are N trials, times 0.2, that's our 1 over 5 to the power of 0, times 0.8 to the N minus 0, again because these two exponents must add up to 1. Sorry, not to 1, to the number of trials. Right, and the probability that X is 1 will be N choose 1 times 0.2 to the 1 times 0.8 to the N minus 1. Okay, and that's all greater than 0.9. Alright, at this point, I want you just to remember your combinations formula. So NR, N choose R, is equal to N factorial over R factorial into N minus R factorial. Okay, we're going to use that shortly. Alright, so keep that in mind. I'm just going to put this on the side over here. Oh, look how neat that was. I'm so impressed with myself. I should become an online teacher. Alright, so moving on swiftly, we can now look at the calculations separately. Alright, so let's look at the probability of X equals 0 first. Okay, so in essence, I'm working with this one now. right? The probability of x equals 0, which, as I've shown above, is n choose 0 times 0, 2 to the 0 times 0, 8 to the n minus 0. Expanding that, if we now use our combinations formula, we're going to get n factorial over 0 factorial into n minus 0 factorial times 0, 8 to the power of n. Remember, because the 0, 2 to the power of 0 is simply 1. Okay, we can simplify that further to get n factorial over n factorial times 0, 8 to the n. And obviously this is going to equal 1, so we're left with 0, 8 to the power of n. Okay, let's look at the next one. So I'm going to just erase this now out the way and work on the left-hand side here now, on the right-hand side, sorry. And that means we're now working with the probability that x equals 1, which, as we've said, is n choose 1 times 0, 2 to the power of 1 times 0, 8 to the power of n minus 1. Okay, putting that into factorial notation, using our combinations formula, we have n factorial over 1 factorial into n minus 1 factorial times 0, 2 to the 1 times 0, 8 to the n minus 1. Okay, so now if we expand just this section, all right, we know that n factorial means that it's n into n minus 1 into n minus 2 and so on until we get to 1. All right, over 1 factorial is just 1, but we have n minus 1 into n minus 2 into n minus 3 and so on all the way to 1. Okay, so you can see some cancelling happening here. The n minus 1s will cancel, the n minus 2s will cancel, and basically everything's going to cancel except for the initial n on that side, because everything in between will cancel until we get to the 1, which will also cancel. Okay, but remember, we still got the 0, 2 to the power of 1 times the 0, 8 to the n minus 1. Okay, so tidying that up, the n cancels, so we're left with n into 0, 2 to the power of 1 times 0, 8 to the power of n minus 1. Okay, we can multiply out to get 0, 2n. Then split the exponents for the 0, 8 to get 0, 8 to the n times 0, 8 to the negative 1. Okay, developing that further, we get n over 4 times 0, 8 to the power of n. Okay, that n over 4 came just by multiplying the 0, 2 to the 0, 8 to the negative 1, which becomes 1 over 0, 8. Right, on the next slide, I want you to realize we're going to be using that solution and plugging it back into that and into that in our original formula that we set up, which was this one. Right, so substituting in, we get 1 minus 0, 8 to the power of n plus n over 4 to the power of 0, 8 to the power of n, to 0, 8 to the power of n, and that equals, well, is greater than 0, 9. And from here, it's a little bit more simple to solve, so we're going to have negative into 0, 8 to the n plus n over 4 to the 0, times 0, 8 to the power of n will be equal to greater than 0, 9 minus 1, which is negative 0, 1. Divide by the negative on both sides, so we get 0, 8 to the n plus n over 4 times 0, 8 to the n. Change the direction of the inequality and get 0, 1 on the right hand side. Now factorize the 0, 8 to the n out, and you're left with 1 plus n over 4 is less than 0, 1. simplify inside the bracket, get a common denominator of 4, which means you have 4 plus n at the top, and that's still less than 0,1. And you can now multiply both sides by 4. So we get 0,8 to the power of n into n plus 4, just put in the variable first, which is now less than 0,4. Right, now at this point it's not possible to isolate n in this inequality, so the only thing we can do is substitute different values of n. Remember, n represents the trials, so it has to be a natural number. So we're going to keep substituting different values until that we see the inequality doesn't make sense anymore or is contrary to what it's telling us is there. So when n equals 17, all right, so if n equals 17, then on the left-hand side, we get 0,8 to the power of 17 into 17 plus 4, and that gives us a total of 0,473, which is more than 0,4. All right, then let's try when n equals 18, and I've just chosen random numbers now. You can test it out on the calculator and see where you have to kind of start writing down solutions. Maybe like in this example, I've already tested that 18 is the change over, so just put the 1 before, just so that you're showing some working out. Okay, so if n is equal to 18, then 0,8 to the power of 18 times 18 plus 4 gives us 396, which is less than 0,4. So in other words, the first natural number that satisfies this equation, or this inequation, is 18. Any natural number after that would also solve it. So if you had to try 19, 20, 21, all those answers will give you values that are less than 0,4. So our final solution then is that n is 18 or more patients. Okay, and if you go back and look at the question, you'll see what the context of that means, to remind you. All right, last notes that I have for you is if you turn to your page 132 of your green statistics and probability book, about a third of the way down the page is a heading that says some additional notation and notes. I'd like you just to read through that. It's kind of a summary of what we've been doing, and that continues with your exercise 1 on page 133. I would suggest you work through that exercise over the next couple of days so that you are ready for your test on Friday.